a different solution. Okay, yeah, well, let's start. So thank you, Subhroneel, for continuing your lectures. And yeah, the floor is yours.
Thanks, Sen. Okay, so this is the second lecture. Last week we discussed that in 4n+2 space-time dimensions with Lorentzian signature, you can have 2n+1 form, on which you can impose the self-duality or anti-self-duality condition consistently. And hopefully I convinced you that the free field theory of this definitely exists because we define them through a Chern sequence in the bulk. That these, at least the free theory can always be defined as the boundary dynamics of a specific abelian Chern sequence theory. And I ended by writing down.
So if it's Euclidean, then it's 4n.
That is 4n. Yeah. I should say that this is true for real forms.
Yeah.
If you are allowed complex, then of course you can have 4n imaginary examples. And I ended by writing down the action which was written down by Ashoke Sen. And so let me just write it down once again. So here P was a 2n form.
So really, it's completely out of focus right now.
Oh,
Let me just. Is it better stand?
No. I think that will just switch to the integrated camera, then to the camera again, like in the middle. Just try to switch the camera.
No, in this video. No, I think just use the drop.
Yeah, it's better now.
It's better now?
Yeah.
Okay.
Yeah, that works. Yeah.
Okay.
Second. Thank you.
No problem. So we wrote down this action. So P was a 2n form. Q is a 2n+1 form. And Q, by definition, satisfies Q equals to star Q. So this is by definition. So it's 2 even offshore. And I told you that this formalism, which is due to Sen, has several unusual features. There were two unusual features that we discussed last time. One in great detail, which is the fact that Q itself is being treated as a dynamical variable. Even in the standard formulation, the 2n+1 form is typically interpreted as a field strength. So typically we think of Q should be given as D of some potential, but we are not going to do that here. Q itself is being treated as a dynamical variable, and by a slight, so typically we call it field strength like field, but field strength like field is a mouthful, so typically I will just keep on calling it field strength, even though keep in mind that Q is not to be thought of as D of something. So, and I also motivated that while this is a sort of non-standard thing to do from a QFT perspective, it's a very expected thing from a string perspective. The Raman sectors typically coupled to field strengths, and the propagator is that of the field strengths, and so on and so forth. The second the unusual feature which we discussed very briefly is the fact that the action has an additional field, P. So remember the equations of motions that you can derive from this action, we showed that you can massage them into this form, so the equations of motions of P and Q completely decouple, even though it looks like there is a kinetic mixing term present, but at the level of equation of motion, the P and the Q completely decouples. This is the one that we are after. This is the physical sector, and this is an additional sector. And even though P is not an auxiliary field, it has dynamics. This is of course a dynamical equation of motion. It has a kinetic term. We say that this is introduced only to sort of write down a covariant Lagrangian on an action, but at the level of equation of motion, they completely decouple. And today's lecture will be to show you that this decoupling continues to hold true, not just at the level of equation of motion, but at the full quantum thing, even in presence of interaction. So that will be the goal of today's lecture. So I should just maybe say a couple of words about this, why the extra field is expected from string theory perspective. Because once again, from a field theory perspective, this seems like a little strange thing to do. I want to describe or I'm interested in the dynamics of some degrees of freedom, but then I'm introducing additional degrees of freedom. And these are really degrees of freedom because P is not an auxiliary field that you can just integrate out. And the reason for that is that so very shortly, this problem had a sort of bigger version of the problem in constructing space-time actions for string theory, what is called the string field theory in type 2 sectors, especially type 2B. And the problem was for writing down a kinetic term for all Raman fields, not just the massless ones, but the infinite power of the massive fields. So there was a problem in writing down the kinetic term. And in fact, that was the problem which was solved by Ashoke first. And massless sector is essentially just a sort of special case of that infinite computation. And the way it was solved involved introducing an additional string field, which nicely decouples from the physical string field which we are after. So it's not a surprise from the string theory side that the field theory also inherits this feature. So even if you want to just describe the round 5 form in type 2 this probability, the kinetic term would involve an extra additional field, which would then decouple. So that's one thing. Another motivation comes from the fact that there was a paper a few years after Ashok wrote this. I think it was by Zeman, Rees, someone else, I'm forgetting, who essentially showed that there's a sort of mathematical formalism that underlies any classical action that you can write down, which is known as the homotopy algebraic formulation or the homotopy Moria-Carta action. So essentially the point is that every action that you can write down can be recast into a standard mathematical form called homotopy Moria-Carta action. And the only difference is that each action comes with its specific representation of the homotopy algebra, which goes into this action. And what they showed is that if you just simply take the algebraic data of trying to write down a kinetic term for a self-dual form field, then you would naturally end up with something which is essentially a Ashok's action up to some frequent definitions.
So the trick, did I understand correctly? The trick is that if you try just to do everything with a dynamic subdual form, you can't write down a kinetic term, or you have to break covariance or whatever.
Right.
So now you're introducing an auxiliary subdual field.
Yeah.
It imposes the constraint of self-duality on the dynamic field or something like that.
Yeah, no, it's not exactly like that. That's the approach which is taken by PSP or the other approaches that are known from the 90s. The approach taken here is that the additional field is not really auxiliary, it is really dynamical.
No, I'm thinking of Q as the auxiliary field.
Q
doesn't have a kinetic term.
That's true, but you say that the dynamics of Q is precisely the equation that you would expect for the self-dual form field.
Well, it doesn't come out of. So yeah. DQ comes out, but not.
But you would not expect second derivative of Q because Q is already like a field strength in some sense. So its equation of motion should really be first order in derivative.
Yeah.
So the trick essentially is that if I somehow focus on just the self-dual part, then I really don't have a, let's say, fully satisfactory action. I can write down an action, but either it ruins manifest covariance or it introduces infinite number of auxiliary fields or auxiliary fields in a non-polynomial way, so on and so forth. But somehow, if we augment this by an additional dynamical field, then you can write down a fully manifestly Lorentz invariant action, with which you can do classical and quantum computations both. I've still not talked about the quantum theory, but that's what we're going to do.
And I guess the PQ notation that also smells like a canonical pair almost.
Almost, but not quite.
Yeah, not quite, I mean, clearly we're using these letters because there is something, this is like a computer, like.
I'm using PMQ because Ashok uses PMQ.
Yeah, but I think actually Chuck used that notation precisely because.
Yeah, in some sense, but not quite. We will see what the canonical pairs are.
There's of course, because now it has to be self-relative and so on. Right. But so the second motivation, so the first was string theory, the second was Zeeman and homotopy algebras from classical actions.
Right. So,
but that where's the lead in that? What exactly is new in formulating with homotopy?
There is nothing new in it. It's just a recasting of the standard way. But usually, when we construct action, we don't start off by constructing it from the homotopy algebraic perspective. Typically, someone gives us an action, and then we read off what is the infinity algebra underlying that action. Right? But you could always reverse engineer it. Somebody could give you the full chain complex, which is your BV space, right? Field, antifield, everything that is given to you. And then you could say that, okay, fine, if I have the full BV complex, then I could try to use what infinite algebra is.
Okay, so
and write down the homotopy Noriega action for that.
Okay, so the lead is that when you are inside this, chain complex and so on, then naturally you're led to this form.
Exactly. So if somebody had already thought in that line, somebody would have just discovered this much earlier, in some sense.
But if I vary with respect, take the equations of motion, which is pick the P, I get d star dp is equal to dq.
Yeah, so there was something that already went in last time, so let me just quickly.
I wasn't here.
Yeah, I can show you what went on. So if you just vary with respect to P, you get this.
Right.
And if you vary with respect to Q, you get this.
Right.
Now I can take a D of this second type.
Okay.
Which is just d star dp equals to 0.
I see.
And then substitute bracket here.
Okay.
But you're right, I mean, this is not something that immediately follows. There are few lines.
Wait. Don't erase.
Okay. So I took a D of this guy, which gives me d star dp equals to 0, and then I plug this back into here to get the.
There's two black holes. You don't have to.
Yeah. But I can erase this part, right? This is very trivial stuff.
Should the P be interpreted as D of some C or not?
P itself is like a C, right? It's a 2n form, and it emerges as a dp. So P itself is like a potential, so to speak. But one we are not interested in, right? Okay. Now, at this point, it might be quite tempting to think of as P as my unphysical field and Q as a physical field. But this dichotomy, this nice clean separation between P being unphysical and Q being physical, is something that only works in flat space in absence of interaction. So this is kind of misleading to think of P as the extra field and Q as the physical field, so to speak. Q is indeed the physical field, but what is actually the extra field, once you turn on interaction, turns out to be not just P, but something that, I will define it H subscript S. And I will define it like this. And you can see that this equation simply implies D of H is equal to 0. Is it something that's clear? If I just take a D of H's, this term identically vanishes, this term dp is 0 and D of Q is 0, so the equation of motion simply implies D of H's equals to 0. But also note that by definition, H's is also something which is self-zero. And at the level of free theory in flat space time, this extra step makes no sense. It's just something you can do, but you could very well not do it and simply work with what you have, what I wrote down earlier. But once I turn on interaction, you will see that this is the thing that makes sense. And when we do the Hamiltonian quantizations, we will see that the extra additional field is also something which is a self-dual object. So, in some sense, this theory is a theory of two self-dual functions. One of them we are interested in, one of them is just something that we needed to introduce to write down a covariant action. Okay? Okay. Now, let's quickly turn on interactions. So let me put a subscript 0 here to indicate that this is the free term of the kinetic term, so to speak. And so that I don't have to write this term again and again. And the interaction that you would like to turn on as a specific form like this, we are putting essentially a single restriction on the kind of interaction that we want to put in, and the restriction is as simple as that. That this interaction Lagrangian of the action, which you will want to think of as, it depends on Q and not on, and of course it also depends on any other fields you want Q to interact with, which I am collectively calling by some phi r uppercase. So the philosophy is this, that this free theory is a theory of two chiral bosons, two self-dual form fields. I'm interested in one of them, so I'm going to turn on interactions for only one of them. The other one, I'm not going to introduce any interaction at all. So that one is going to remain free, trivial. This will help me in sort of in the full Hilbert space. This will help me in sort of isolating what is the Hilbert space of interest to me, the one which is interact. And there will be always something that is a free Hilbert space coming along from the right, but it will be easy to just forget it, project it out. Okay. So this is the only restriction you are imposing on the Lagrangian, that it can depend on Q. It can even depend on Q through derivatives of Q. By the way, I'm just, if it's not clear, it can also depend on E of Q, or whatever interaction terms that you want to impose, right? But not on P, that's the important part. Can't have anything to do with P. And of course, it can have other fields, because typically self-dual form fields don't interact among themselves, they will couple to something else. Like in supergravity, we'll have some Chern-Simons, that kind of terms, or other kind of terms, and etc. And of course, I mean, if you want them to be some sort of classical background field, you don't give them kinetic term. But if you want them to be dynamical field, then you turn on a kinetic term for the phi's as well. Whatever is the appropriate kinetic term for those fields. Okay? So it's a very sufficiently general thing, and this will be a recurring theme again and again, that because we have introduced this extra additional field, whatever analysis we do, we have to always keep in mind that this extra additional field should be something that should trivially decouple from the dynamics at all levels. So all our formalism is going to be guided by this, this motto, that we have introduced an extra additional field, but it has dynamics. So somehow we need to make its dynamics completely trivial at all levels, at all times. Okay. So the claim is that if you impose only this restriction on the interacting Lagrangian, that the claim is that achieves the trick. So the level of equation of motion, this is quite easy to see. So in presence of this term, so the equation of motion you see this one doesn't change, right? So I still have this, but this one now gets an additional contribution because I'm varying with respect to Q, and this guy depends on Q. So I have, and since I'm not going to specify what this is, let me call the variation of this with respect to Q some capital R. This is going to be typical, some functional of Q and size. The only thing I can tell about R is that R is going to be antecedent. That follows simply because of the fact that this is being varied with respect to a self-dual form fit. It's a Lorentz invariant object which is being varied with respect to a self-dual thing, so it's going to pick up only the antecedent piece. Other than that, of course, I don't need to specify anything more than that. But of course, if you give me a specific L-hat, you can always compute this, right? It's not a big deal. And now we are once again going to sort of do something similar that we did for the fit case, right?
So you wrote into self-dual?
There's a minus sign.
Yeah.
Yeah.
So you say when you vary a self-dual, you get
You get the anti-self-dual space, just like here, for example.
Oh,
right. Because self-dual is
self-dual kills the self-dual.
yeah, exactly. Okay. So the way to do that is that first is that okay, if I take a d of this again, right? I just have this star dt minus d of r to be 0. But then I can use the first equation and trade in dq in favor of dr. And I can think of this as d of q minus r equals to 0. That's one equation. And this equation, since it has not changed, is essentially still going to be equivalent to what we had before. And notice that the first one, so once again we still have two self-dual form fields in our theory. One is Hs and one is Q. But this one is free, whereas this one is interacting via some interaction term R, which you can always compute once you have specified what interaction you've turned on that direction. So at the level of equation of motion, the decoupling is once again very easy to see.
What is the index? S of 5 or what is it?
It's it's not an index, it's a subscript, it's a name.
Yeah.
I cannot justify the name right now, but I will justify it next lecture maybe. Okay, very simply speaking, this guy is basically going to be like a singlet.
Yeah.
Somewhere down the line to a lot of transformations, so that's why.
So it's not in honor of the speaker.
No. All good. Okay. So then is the last line good?
Yeah.
Sorry.
Yeah, that's fine. I'll just list the comment.
Okay.
Don't mind me.
Okay, so one example, it's not really an interaction, but like a very quick example to just sort of emphasize what we did right now, and also something that will be useful to us when we discuss specific computations later on, is that the special case when you have some classical sources turned on, And in that case, we have the free action as usual. And the L hat is expressed like this. Now there are two subtleties here. Typically, when we turn on sources are turned on with respect to the potential. Here we already have something which is not a potential, a field strength like radial. So this K is not something that is immediately obvious that how is it connected to the classical sources. But in principle, the only kind of term we have a field strength. Was there some question?
No.
Okay. Is another 2n plus 1 form some K like this? So let's work with it and let's see how we can connect K to the sources that we are familiar with. So right now K is some 2n plus 1 form. Okay. And this equation has once again is completely insensitive to what kind of interaction you have turned on. So that equation is still true. You still have P of H's equals to 0. But the other one, you can show this reduces to this, where K plus minus are essentially the self-dual or the anti-self-dual projection. Okay. We can make it look a bit more like the source equation of motion if we just from here use the fact that d of k minus, you can simply write it as dk plus. So probably be some, yeah, right? Because I can write k as k plus and plus k minus. I take a d on all sides and I just bring one on this and one on here. And then what I can do here is that I can write. So what we can do is that let's say define q plus k plus to be some q hat. This is still self-dual because k plus by definition is the self-dual part of the k. Q is of course by definition self-dual. So q hat is also star of k hat. And then essentially what you have here. So what we are doing here is that we are adding k plus and subtracting k plus on this equation. Let's add k plus and subtract k. So q plus k plus I'm going to replace by q hat. And once I have added k plus here, subtracted k plus, so it's basically k minus plus k plus. So that's like a dk. I can bring to the other side.
Sorry, how did you get the q minus k minus equation to
so this one I just wrote as q plus k plus minus.
Yeah, before me, but how did you get the first one?
This one?
Yeah.
This one is because if I vary with respect to, so just look at there, this r.
Yeah.
Right? R is what you get when you vary the interaction with respect to q.
But so where's r now?
So this is the R. The
R
R is
okay,
like
you have not included the r. Yes.
No, I have.
Yeah.
This is the L hat. So R is whatever you get from L hat when you vary with respect to Q. When I vary with respect to Q, I get the anti-self-dual part of this, which is by definition this K.
So in the Lagrangian, there is no k plus.
In the Lagrangian, there is no K plus. That's right.
But you're adding it.
I'm adding it just to make it look like the source equation that you would be more familiar with. You don't have to. You can stop by directly.
Right.
But
I mean, can you add anything there, or somehow is it tied into k minus in some other way?
If you do not add something which has the interpretation, so there are two things. One is that it has to have a self-dual part. such that this combination is still true. Sure. Another thing is that something which combines with this to give me an exterior derivative of a general form. And that kind of uniquely forces me that K plus is the only thing that I can write down.
Well, I mean, I don't know what K plus is if it's not in the Lagrangian. So you know, either it's given somehow from K minus, so through some other procedure, not duality.
So I will tell you what K is in a moment. But at this moment, if you just want to work with K minus and stop here, that is completely fine. Yeah. The rest of it is simply I'm rewriting this whole thing in a way, cosmetically, such that it looks something that is more familiar from the way we are used to doing field theory.
Sure.
Which is not the way you should do really when you are doing this formalism, but just to sort of make a connection.
But why is L hat not in your action now? You have added sources, but where is L hat?
This is L hat.
Where I don't see L hat.
It is.
Oh, okay. So L hat is by definition. So it's a special case of L hat.
Yeah.
Okay.
So yeah. This is like the simplest.
Right. Yeah, but I mean, in general, we have more than that.
Of course.
Yeah. So that's.
Yeah, this is just an example.
Yeah. So this is okay. I wouldn't call that L hat. That's just.
Yeah. But I have not told you that what K is, right?
Yeah.
If K is some sort of like complicated objects of some field, and then I turn on the magnetic. Then this is an L hat. Right now it looks like an external source that I've turned on.
Well, if L hat is linear in phi.
It doesn't have to be linear on phi.
Yeah, if it is.
If it is linear on phi, then I mean it's something simpler. I don't even
I mean the source should not depend on
So this is clearly linear in Q, but the other fields I'm not saying anything about.
Oh, sorry, I mixed your Q to phi.
Yeah. I know, I understand. I got problems.
Yeah.
But yes, of course, I mean, general interactions would be much more involved than this. Like you would have Q squared and other field squares and PQs and so on. Sure. Okay. Okay, so this is what we get, and this, of course, by definition also means D star Q hat D of K. And why am I saying that this is more sort of familiar with it? Because remember, if this was really a field strength like variable, then you would prefer to write this if you have a source J. And now you have a sort of way of interpreting that what the connection of K is with respect to the J that you would turn on in the standard way of doing, say, supergravity. And simply, so in the standard way of doing supergravity, F would be some, potential, field strength of a potential DC, and we would turn on a source term which would look C with star J. So that's the analogy that I'm drawing here. But this J is a conserved current, right? Which means typically with the sources, background sources which are some conserved current, which means that locally, because we are in flat space time, it's true everywhere, but at least locally you can always solve it in terms of some K. So it's that K which is a K. Okay. But you don't have to do any of this, because trying to sort of make this connection is something to, just for familiarity, but in reality, this is enough. You can just stop here. The reason I introduced or I just discussed this example is that we are going to revisit this example once I tell you how to couple to gravity, not in this lecture, but in the next one. Simply because terms such as this do appear in supergravity, right? In fact, this Chern-Simons terms is of this kind. Like think of this K as the B2 field and the three form flux. This would precisely be the Chern-Simons terms, and we would precisely have this kind of terms present in the type 2 supergravity, for example. So just to sort of set the stage a bit, and we are going to see them again. Okay, so this is all that I would say about the classical analysis. Now we are interested in the actually challenging part is that if I want to now quantize that theory, like I have the free part given and then there's some L hat that is given to me. Nobody has specified what L hat is, but suppose somebody has given some L hat to me. Then I want to do a Hamiltonian quantization or covariant quantization of that, canonical quantization of that. And I want to show that it leads to a nice clean separation at the level of the Hamiltonian itself. That it nicely separates into a Hamiltonian of a free chiral boson, free self-dual form field, and another self-dual form field which is not free, which is interactive. So if we can achieve this at the quantum level, then this formalism is something that is really good for doing quantum theory as well. If it is not, then all this was for in vain, because this is just another way of writing the classical equations for motion, which we anyway could have written down. Or there are other formalisms which also does this just as well. Okay. So just for pedagogical reason, let us focus on d equals to 6. Simply because canonical quantization cannot be done unless you sort of start writing down indices and so on and so forth. And writing down .2n plus 1 every time is going to fill up the boards and just do one thing. But then you might ask that why not d equals to 2, which is the simplest case. Simply because d equals to 2 is a bit simpler, there is no gauging variance there. So d equals to 6 is the first lowest non-trivial dimension, which has all the features that you would expect in any general dimension. The only thing that would change is that you have more and more number of indices. That's it. But conceptually, everything that we are going to do in d equals to 6 is true in any d equals to 4. It's easily extended. And so, but by the way, in Ashoke's paper, he does it for full d equals to 4 plus 2. So it's if you just want to go and look it up, you can. And so he would have something which is E form field with 2n indices because it's a 2n form. I'm going to instead have something with 2 indices and I'm going to call it capital B. And he had a Q which would have 2n plus 1 indices because it was a 2n form. You would have something which is 3 indices and I'm going to call it F. And this is the dictionary. At any point, whatever analysis we are discussing here, you want to go back and compare it with this paper. You just do this. And of course, correspondingly with the canonical conjugate momentas and so on. It should be enough. And also remember that F equals to star. But the star is now with 6-dimensional Minkowski. Okay. So we are interested in doing a canonical quantization. So a nice way to do is that first you just simply work with the independent components. So this new 6-dimensional indices, we are going to break into 0 and I, where I runs from 1 to 5, and 0 is the time indices. I mean, that's the price you pay for doing canonical quantization. You can't have Lorentz symmetry manifest anymore. So you have Bij, but remember this is a 2 form. So Bij and Bji are not really independent, right? So one way to make sure that we are only working with one of them and not the other, because otherwise you're going to overcount your phase degrees of freedom, is simply by restricting this set Ij to sort of freely run in such a way that I is always less than j. And then I can go as low as 1j and go as high. And of course, you have the other one, B0i, or Bi0, whichever one you work with, doesn't matter. So this is for the B. And then we have the F. This has two kinds of term. One is 0 I1, or you can have I1. And once again, all these IKs are always going to be subjected to this kind of restrictions from now on. For the purposes of this lecture, I's and J's, in any form they appear, they're always going to be like this. Okay, that will help me knock over down. But you see, these two are really not independent. And the reason for that is this. So you really don't need to work with both, just need to pick one. And we are going to pick. Yeah. Okay. So one other thing that whenever I'm going to write down some summation over these i's or the j's, that summation is always going to run over with this restriction, but I won't write it again and again.
Well, it's nice that 5/2 is the same as 5/3.
Sorry?
It's nice that 5/2 is the same as 5/3.
Yeah. Okay. So
I choose. That's what I don't get to be.
yeah, I think I need to do this. Otherwise, this was not okay. Okay, great. So just to have it somewhere, remind you that in our new notation, here is the action that we are working with, and all of this is implicit in D equals to 6. The same action that I wrote down earlier, the squeeze up or these and Great. Now the first step, I mean, everyone knows canonical condensation, so I mean, don't worry about it. So the first step is essentially to sort of write down this nice looking Lagrangian, but only in terms of this independent variables, so that when we go to the Hamiltonian, we know that we have the correct phase-space degrees of freedom, not about counting of anything. But it also means that now the action is going to look ugly. But that's the thing. So the Lagrangian density looks I can't go on the right of this page. So And finally, this is straightforward but tedious. It's just breaking it down into components, getting rid of the extra things in favor of the ones that we've chosen to work with, and then just doing a little bit of algebra to get to this. All the sums of ik's and ij's, and I'm even dropping the subscript k's and etc., are always on that particular range. Remember that. And L hat is always a functional only of if and phi, right? So I'll wait until you have copied it down, but then I'm going to make some observations. Please let me know when you finish.
So it doesn't really affect anything that you made a choice of the components of F to work with.
No.
One, you know, if F would have been dynamical, then you would have in the df expressions, you know, then you would either have time derivatives or not have time derivatives. But here
it doesn't
it
matter.
doesn't matter.
That because that part is essential, that you're working directly with F itself as a dynamical variable. If you're thinking of F as BC, precisely the point that you made would have made a huge difference.
Yeah.
Right. Did everyone understand? So can I continue? Okay. So the first thing to note on this huge horrendous expression, which is essentially the same thing that is written nicely up there, is that no time derivative of this guy appears. B0i. Right? B0i does appear, but it always appears with a derivative with some special dimensions. And we all know what this means, right? The canonical conjugate momentum has to be identical to 0. So, which we are going to denote by this. And this is what is called a primary constant. Because this is true even without any using any equation. It's just true on the structure of the action. So for the students here,
I guess to link to the comment that Richard says with choosing the other f, then you're probably just moving the epsilon symbol from that term to the other term over there.
yeah. But I can always do that.
Yeah,
I can always do
that. Okay, yeah. Primary constraints.
Yeah. For the students, everyone sort of remembers a little bit of like canonical conversation with constraints, right? I mean, so I mean, it's not like you need to know a lot,
Yeah.
but I mean, in some sense, I will cover it in such a way so that you can, take it along as it go. The second point to observe is that no time derivative this guy. Right? Which means conjugate momentum defined. Okay. So both of these are primary constants because both of them immediately follow from the action itself. Now it can't be that. So basically, you see, we are basically working with three position coordinates, so to speak, like dij's, dcy's, and if ijk's, right? Two of them turns out to have no conjugate moment. So it better be that the third one's conjugate moment also doesn't vanish, right? Because then it means that there is no dynamics. So of course, the third one thankfully doesn't vanish. So the only non-trivial non-zero momentum that we have is a non-zero identity, and we can compute it, right? We know if this expression is given, just computing the partial derivative, and essentially you're going to look into all the terms where you have the zero b moment, right? This one, and then write it down. So the expression for this. And at this point, the notation I don't need this anymore, which is essentially that whenever I have what's a nice term like this one, epsilon with this contraction, I'm just going to sort of the epsilon and the f's dummy indices, I'm not going to write it down. And I'm going to do it for anything with a 3 index object. So anytime I have an epsilon with a 3 index object, it will be a 2 index object, and I'm going to just write it as epsilon this with the 2 indices explicit. Because otherwise, I mean, I'm going to run out of spaces like very soon. And it makes no sense. It's a very trivial shorthand notation that you can make.
Could define some star, 5-dimensional.
Yeah, I can define a 5-dimensional star, but I don't want to, because it might be a confusing, because there is a 6-dimensional star we need to think about and so on and so forth. I thought about putting a tilde on f, but then I thought that, I mean, it might be good to remember that there is an epsilon, so that when someone is doing the computation first time, it helps to remember all these things. Okay. There are going to be some tedious steps here. I would implore you to not get bogged in the sort of things of substituting long expression into long expressions, and sort of focus on the logic, because the algebra is really straightforward. It's just, you know, doing.
I'm a bit curious about the sign. So the first term in the Lagrangian, we have the d0 b squared. So it's like the kinetic energy. So
yes.
you would guess it would come with a plus.
No, it would be minus. It would turn out to have a wrong sign.
Yeah, so it is a code, but it is a free code.
In some sense, yeah.
So how do I know that, you just wrote it down, so how do I know it should be this way?
Oh, because where is the covariant expression? From here. Just simply starting from here, and my matrix signature is minus plus plus plus.
So what if I put the minus there?
Oh, you can, but then much of this analysis that is going to sort of walk through is not going to go through.
And what is it?
The Hamiltonian has to nicely split, and this splitting won't happen. This sign is important. Can't just arbitrarily choose it. One thing that you can do is that you can change the sign here and then on the other one.
Okay.
Right? Forget about this L for the time being.
Yeah.
Then effectively, in some sense, it's essentially sort of switching the role of whether you're calling the Hs to be the physical field and the Q to be the unphysical field. The other way around. Then you would turn out the interaction for the Hs, not the Qs. That you can do, but can't make both of them same sign. Then the decomposition doesn't work anymore. So we have our momentous, we have our Lagrangian. Now we can just simply do a Legendre transform and write down the Hamiltonian density. And I'm just going to directly write it down. See, this is the only PQ dot term that you have, right? All other momentas are identically zero. Right? So this is the only PQ dot term. And then you would write down this L, and this essentially after some algebra. Oh, by the way, I should have maybe told earlier that this symmetrization and anti-symmetrization, my weight is like there is no 1 over p factorial. Okay, so if you have, del mu of nu and anti-symmetrized, it's del mu nu minus del mu nu, no half. So that's the convention I'm using. I don't think I said it anywhere.
Okay, in your commutative.
In the brackets, yeah, because I'm really writing them, so I should have. Okay. Okay, another thing that I should have said is that I do have this L interaction. So there is some degrees of freedom phi sitting on there. But I'm kind of only doing the canonical conjugate momentums of the PQ sector or the FB sector. So very strictly speaking, this is not really a Hamiltonian, but what is called a Rothian, right? It's kind of a mixed object which lives on phase space and the configuration space, etc. But then the whole point is that you understand that we need to sort of realize the separation for the FB sector. That's a subtle sector. Right? The other one is a sort of very standard thing. So we don't really worry about that. So it's okay. It's up to whatever. But then this is just a point to mention. Okay, so we are in the first step that we have written down the Hamiltonian. We have identified two primary constants, which is two momentums being zero. So my phase space is going to be labeled by these three field variables that I've chosen: B0is, Bijs, F and their canonical conjugate momentum partner. But out of these 6 phase space quantities, 2 of them have to vanish. 2 of the momentas have to vanish. So these are primary constants, right? So which means that to quantize this theory, I need to perform covariant quantization, canonical quantization with constraints, the Dirac analysis. Right?
Oh, so the Rothian, that is the capital 5 you're talking about that? Was that the one which you're not making Hamiltonian sector?
Exactly.
Okay.
Yeah. Out of the 5 sectors. If the interaction is just involving Q's itself, then of course this is fine. This is okay. Another thing I should mention is that for now, I'm going to, this is just a simplifying assumption. I'm going to think of really that this interaction depends through Q, only through Q. Non-derivative dependence appears in any interaction. This is just a simplifying assumption so that we can get through it in one lecture. That's it. All of it that I'm going to say holds, nothing sort of goes wrong if you involve a derivative expansion. You just have to have a few extra terms and do an explicit over manipulation. It's just a sort of simplifying assumption.
Right, but okay, but Q.
In the interaction, I told you that the only constant is
but Q is
sorry, Q, not Q
is F, right?
F.
F, yeah.
That's right.
But if you have df, then there could be 0 components of that. There could be there would be velocity fields. That's not good in Hamiltonian.
Yeah. So if I involve d of f in the interactions, I will have to do a little bit of more algebra. But I'm saying that whatever I'm going to show goes through. It's just that it's going to take us considerably much longer time, and we are not going to gain anything conceptually. And another thing is that at least the known examples where self-dual form fields naturally appear, the interactions you can always express directly in terms of f's, not put another derivatives on f. So for all the cases of interest, this actually already covers it. Okay, so now we are at the second step. The first step is typically to write down the Hamiltonian and identify your primary constants. And the second step is typically that if you have this primary constants and see these constants are true without using the equation of motion, also, which means that this has to be true at all times, which is something that I can evaluate, right? I can simply take these pi's, take a time derivative, and see if they are 0 or not. If those time derivatives are identically 0 or equal to or proportional to one of these constraints, then that does not give me any new constraint, which is fine, which is we are lucky in some sense. But if it gives me some new function, then we have to set those equal to 0 as well. And these are called secondary constants. And then those secondary constants time derivatives should also manage, give tertiary constants and so on and so forth. And we have to keep on doing it until essentially we stop. And we will stop, right? Because the phase space is finite dimensional. So either you have all constraints and there is no dynamics, or at some point you stop this process. So the first, let's take a look at pi v0 i. We're interested in time derivatives. So this is also bracket with this Hamiltonian. Okay, it's actually given with respect to the Hamiltonian, not the density. Remember you have to integrate over the spatial coordinates. Yeah, I am assuming everyone is sort of familiar, like the curly is the density and the straight lines of the Hamiltonians. And this, see, pi b is the canonical conjugate to del, so b0i, right? It's only going to hit the Hamiltonian whenever there is a b0i sitting. And where is b0i? There is none here, there is one here, there is one here, and there is none rest of the place. And wherever there is a b0i sitting, the thing that is sitting in front of it is essentially, sorry, there seems to be some sort of double writing of some kind. Yeah, I should not have this. Sorry, this is the only thing. Sorry, because otherwise it just cancels. You know, the same term with the minus and the plus something. Okay, now I wish it was an iPad, I could just less one. Okay, so this is the only term where it hits. And you see what is sitting in front is this pi b I1 I2. But this guy is not identically 0. This was the only non-zero momentum we had. So this is going to give me proportional to, and in fact, it's not going to give me proportional to just pi b I1 2. There's a derivative here. That space derivative is not going to come and hit this pi. It's going to be del pi b some ij. And now we have to set this one to 0. So this is a yes. Yes. Okay. Now at this point, I'm going to define two new phase space variables. Just do a variable change in the phase space. Right now, it's just going to look like some definition, but their usefulness will become apparent in just like 10 minutes. I'm going to define what I'm going to call pi plus minus I just. These are by definition ip plus minus Is this notation clear? Epsilon has all the 5, and then this is exceeded derivative with. I'm just.
Why partial derivative? Why not the d?
It could be a d. Because if you're writing in components, it would be like a partial. That's right. And note that if I take another derivative del I from this, del I by ij of plus minus. Whenever it comes here, it's going to have two derivatives, but all of them are going to be contracted with the acceptance, which means that this term is going to identically drop out. It's going to be 0. And only this one is going to contribute. So this is precisely equal to and the whole point of doing this is telling you that if at one point we choose to work with these phase space coordinates, it's a coordinate change in the phase space, then the fact that this guy has to weakly vanish implies that this guy has to weakly vanish. So you're free to change these coordinates, but then the constants you have to be mindful about. So this constant in this coordinate translates to okay. We'll make use of these coordinates eventually. Right now it's just a definition. And just to sort of tell you that this implies this. Okay. We had another constant, the pi f one. What about that? Now you see pi f has only non-zero points of bracket with f ijk's. Right? It's the canonical conjugate momentum to the f ijk's. So it has to hit all the terms where f ijk's are there. The Hamiltonian, Hamilton is here, this one. And there are quite a few. Right? So it's going to give me some expression. So this expression, just following the paper I'm following, I'm going to denote it as some chi I1, I2, I3, and there's a negative sign simply because that's how chi is being defined. And this chi is not something which is identically 0 or proportional to any of the constants we have found before. It's going to be a leading function. So we are going to get a new constant where chi is weakly vanishing. So this is another secondary constant. And the expression for chi So these terms are the ones where f automatically appears. The last one appears because remember that the L hat actually depends on f. So there are some f's sitting on L hat as well. So the moment the conjugate momentum will act on it, we will pick up a term which is the derivative of that with respect to the f. Okay. We can actually simplify this constant is a sort of looks quite a handful. We can simplify this constant a bit. Because chi is weakly vanishing, acting on it with or contracting it with another excellent tensor would all imply that that is also weakly vanishing. Right? And then this simplifies a little bit more. And also if we use this coordinates, then we can condense some of the expressions a bit. So epsilon chi weakly vanishing ij. This gives us Is this notation clear? Like del F, this is also 3 index object, epsilon is. Sorry, okay. Okay. Now, at this point, you might say that, okay, I mean, there is nothing else we can do, and that's true, because if somebody doesn't give me the precise form of L hat, there is nothing much I can do about this. But there is a simple observation that we can make nonetheless, that if you think of this as a first order differential equation in terms of the variable being f, right? You're trying to solve for f in some sense. Then, sorry, is there a question?
Yeah, why is it pi minus? Why isn't it pi plus? So I'm hitting it with epsilon. I just get delta functions from the first term, and then the dB, I just get epsilon b. So where did the minus come from?
Let's see.
Oh, you get the B.
Yeah, it could be that this one has a minus sign.
Okay. So that would be
Yeah. And that's
this is really the reason why it was useful to.
yes and more. I mean,
yes and more. Okay.
We will see that the Hamiltonian decomposition actually nicely happens in this
Right.
phase coordinates. Okay. So coming back to this point, that if you think of this as a first order differential equation where you're trying to solve for f, you should always be able to solve it for a reasonable function L hat given to you. You should always be able to solve this and solve this, and essentially, write Fijk to be weakly equal to some function. This function is now going to depend on pi minus, and of course the other additional fields phi. The general solution is going to look something like this. So this f, small f, is some function which of course you can explicitly determine once L hat is given. But at least the general solution to this would assume some form like this. We cannot specify what small f is unless somebody gives me an L hat explicitly. But we can definitely say this thing. And this will be a function of pi minus, because pi minus appears here importantly. And of course phi, because phi is there in L hat. That is not going to go. Okay. So this secondary constant chi weakly being equal to 0 is essentially determining your f.
If L hat is some really complicated function, some exponential, whatever, then I guess you would have to do some kind of perturbation theory, expand it in F's.
Yeah, but at least this statement would be true. Like determining this might get convoluted, but some solution we can still implicitly write simply because this is the first order thing. So we started off with two primary constraints, evolved both of them with time, got two new constraints, right? Now it would be really bad if these also evolve with time and we just more new constraints. Bad in the sense that we don't want to work that hard enough, not because the formalism breaks down or anything. Fortunately for us, this is where it stops. So I can write this way. I don't want to erase this yet, but okay, let's work around this a bit. Okay, quick. So is it obvious that there will be no further constraints? Because now you have to evolve essentially this one, chi. You have to evaluate chi dot, and you have to evaluate del I phi I. Okay. So let's say chi. Okay, if you take again this Poisson bracket with the Hamiltonian, look at the original expression. What kind of terms are there in chi? There is a term which is involving say f's, right? It is going to contribute only if the Hamiltonian had pi f's, but the pi f is 0 as a primary constant. So any term which involves f or derivative with respect to f, those are not going to contribute on chi when you take Poisson bracket with the Hamiltonian. But then okay, you have some other terms, right? You have pi b and they all special derivatives. This one would contribute if the Hamiltonian had essentially this what to say pi b 0 I, right? The Hamiltonian is there somewhere, right? Now the top line with the weird gap there.
Isn't what we call pi I J B?
Yeah, sorry. Yeah, you're right. It will contribute with respect to pi I base. So this is the only non-zero contribution that is going to sort of come from this one or this one, right? Because this one is going to hit this one and this one is going to hit the other one. But both of this in turn is going to give rise to terms which is basically proportional to chi itself, because that's how we got chi. So that's not a new constraint. So when we evolve chi with respect to h, we end up with something which is some number and chi itself. So that's why it's not a new constraint. And the other constraint, this one, this is much easily seen that there is essentially not going to be, this is going to be, if you just take the Hamiltonian with respect to it, Poisson bracket, it's going to weakly vanish the image. It's not going to give rise to anything which is proportional to itself. Okay. So the bottom line is essentially that these hierarchy of constraints stops at this point. We have two primary constraints. Their time derivative, we have two further secondary constraints. Their time derivative either gives back the constraints we had before or doesn't give anything anymore. So once you have all the constraints, then in fact the distinction between what is primary and secondary is not really important in the Dutch program. This is something, okay, it's I guess it makes more intuitive sense, pedagogic sense, but what is really important is the distinction between what is called first class and the second class constraint. And just to remind you, the definition of first class constraint is all the constraints whose Poisson bracket with all other constraints vanish. And second class constraints are one whose Poisson brackets don't vanish. At least there should be at least one Poisson bracket between the second class constraints which doesn't vanish. Okay. So let me write maybe all the four constraints together. So I have two of them already written here, and then let me write this. So the other one I'm going to. This was another one, and the fourth one was. However, you want to call it, right? So these are my four constraints, all the constraints that I have on this table. And let's give them some name. Let's call the fact that this is equal to 0 to be some xi. Let's call this one gamma. Let's call that plus minus j 0. And this one, maybe I will call it z1. The reason for giving this shorthand is that now you can explicitly check that if you have a gamma, any of the gammas, and then it doesn't matter whether you put a gamma or a psi, this points of bracket always vanishes. So the gammas are what we would call a first class constant. So this top row is first class constant. But on the other hand, between this and this, there is a constant simply because this is pi f and this is f. So pi f is going to hit on this f, right? So I'm going to get non-trivial points of bracket from the other ones. And it's going to be exactly the canonical bracket, right? Because it's the bond between pi f and the f, which is the non-zero conjugation. It is precisely like P and Q. So it's a delta function essentially. It's delta I1, I, delta I2, J, delta I3, K. That's all you're going to do. So this is my second class construct. Now we are going to use this second class constraint to completely eliminate two of our phase space variables. Because at the end of the day, that's our goal, right? We use the constraints to reduce, because the total phase space was much bigger. That's why we had constraints. So we should try to solve the constraints and come up with independent degrees of freedoms or independent coordinates which would span the reduced phase space, which is the actual physical phase space. So the second class constraints we can use to set pi f to 0 and this fijk to be the solution, like whatever was the solution to this differential equation. We won't be able to write down the solution explicitly, but we know that there will exist some solution and this is being evaluated at that solution. That's the meaning of it. Okay? But that doesn't mean that the second class constraint's role is going to be completely invisible from now. Because if you remember that the correct Poisson bracket on the reduced phase space is given by the Dirac bracket. And that requires you to use the matrix of the second class constraints. Right? So it's going to be present through the Dirac bracket, which will then be promoted to the commutator. So on. So on our Hamiltonian, we are now going to simplify by putting these two constraints. And we are also going to re-express the Hamiltonian not in terms of phi b, but use the coordinates phi plus and phi minus. And when you do that, it's a little bit of long but tedious, but reasonably straightforward algebra. You get the Hamiltonian, the density, to be I'm going to explain what this G is. So I did two things. On that Hamiltonian, I used the variables phi plus and phi minus instead of phi b ij's. So in favor of phi plus, phi minus I created them. And the second thing is that I use the second class constraints to get rid of the coordinates if and this. And this G is a shorthand for this guy. So when you simplify that, at some point you are going to get this combination. You're going to get the derivative with of the interacting part with respect to the field strength square. And then, of course, this L hat term is going to be there. And you have to remember that this L hat is dependent on the field strength or field strength like variable F, right? But now we have to remember that this constraint is being used. And what this constraint tells us that Fijk is completely solved in favor of some function. And remember, this function was the function of pi minus. So it is these things evaluated at that solution. So at the end, this is all going to give rise to some function of pi minus and phi. Once again, if somebody gives me L hat explicitly and if it is not a horrendous function, you can explicitly do this computation and figure out what this small g is. And in fact, at some point when we are going to discuss quantization of chiral bosons on a circle, we will see what g is. We will be able to explicitly derive it and so on and so forth. Okay? But at this point, it is enough for us to realize that this is going to give rise to some function which depends on pi minus and phi, and not pi plus. And we are almost there. You can already see that the clean separation between two sectors are happening, right? One labeled by the phase space variable pi plus, one labeled by the phase space variable pi minus. And the only thing that is ruining that nice clean separation is the last term there.
So the sign of the last term changed.
Yeah, I think I erased the other one. I shouldn't have erased this one.
Okay.
But okay, it really wouldn't matter if this was a plus sign here, because what I'm going to do next. Okay. So at this point, let us take stock of what is the status of the phase space variables and what are the degrees of freedom. Like because we had some constraints, half of them we have already solved explicitly. Remember, we still have the first class constraints remaining. So what is really going on? Maybe I can just do it here. This part is visible. So I had coordinates bij's and then canonical conjugate then. This, in some sense, you have traded for pi plus and pi minus. Because remember the definition there, pi plus and pi minus is some linear combination of the pi b's and the derivative of the b's, right? So using these two coordinates or these two coordinates, in some sense, that's a coordinate transformation we did. It's not equal, but like it's narrow. And then of course you have the other thing, b0 and we have not yet solved the constraints that this is 0. And we have this guy's derivatives. Okay. Now the first class constraints, the reason you the reason you divide between first class and second class, the reason that this is the division which is important is because these two constraints play extremely different role. These constraints are something that you are meant to explicitly solve and then simplify your Hamiltonian, but they make appearance through the correct points of bracket which is the Dirac bracket. These guys, on the other hand, the first class constraints, as the interpretation that these generate the gauge transformations. Okay. Now, what are the gauge transformations generated by these guys? The gauge transformation generated by this one is basically simply saying that you can shift B0i by any arbitrary, some arbitrary tensor alpha 0i, and that is supposed to give you an symmetry. The way to handle the first class constraints, therefore, is to gauge fix. Choose a proper gauge. And then your Hamiltonian would be something which finally is going to make sense. You will have the Hamiltonian defined on the gauge invariant physical phase space. So that's what is basically stopping us from leading to the full factorization. So that's what we have to do now. So this one, it makes sense because you have an arbitrary shift to simply gauge fix to 0. So just get rid of B0. And if you get rid of this B0i, then the last term is gone. Right? So
that's the unitarizing gauge where the pi plus separates.
sorry?
So that's the unitarizing gauge where the pi plus separates.
Yeah, so this is the gauge where the separation is sort of seen cleaned. But if you, for example, one can imagine if for some other gauge choices there are probably some other variables, not pi plus and pi minus, in which you would be still be able to see the separation, but it might look up something. So once we have gauge fixed, do we have a different color chalk? Yeah. Oh, there's a lot. So if we gauge fix this, now you see the Hamiltonian density nicely separates into an H plus and then H minus. Yeah. And that's not enough. And it will now also tell you that because now the claim is that now we have finally found out the Hamiltonian in the reduced physical phase space. Then I should also tell you that what are the canonical brackets.
Don't you want the gauge fix the other guy?
Sorry?
The di pi plus minus constraint that also generates some.
Yes, that does generate. That generates the gauge transformations. Edges and go to
Yeah. So
that's the standard shift one. This
one
one I can gauge fix. I can choose the lambda such that it's kind of like a pure gauge in the BIG sector. And that essentially guarantees that my pi plus and pi minus is kind of gauging unit. So my pi plus and pi minus are now the gauging gradient coordinates of the reduced phase space. That's the. Okay. But yeah, this was a good point. I missed that. Sorry, forward which board was I erasing? Just to remind you that if you have two phase space observables, say F and G, the Dirac bracket between them is the canonical Poisson bracket. Then you have the Poisson bracket with the secondary constraints. Sorry, second class constraints. That's how the Dirac bracket is defined. Right? And you can prove that this is the correct Poisson bracket in the reduced phase space. But this is now being evaluated in terms of the full phase space quantity because it's easier to compute. But this is the correct physical quantity. And then now we have the expression for pi plus and pi minuses. We have the expression for the Hamiltonian in terms of pi pluses and pi minuses. And you can check that maybe coordinates bosons. These are all the so I don't need and let's call them something else. Prime J prime. Is the prime visible or should I use something else? It's fine. Okay. And it's a prime index. Prime, and then this is now for the time being, if you forget about these indices, then forget about this indices here. Then this is exactly the bracket that I wrote down when I wrote down the Hamiltonian for the parallel boson in this Florian-Jakob formulation. So remember last time in 2B, I wrote down a
you had a degree of tensor function.
right. Exactly, phi squared, and then I said that phi is derivative of something like that. And this was nothing special to two dimension. The Hamiltonian description of the chiral boson in any dimension is something that was already known. Always the problem was finding a Lagrangian which is manifestly Lorentz invariant. So this is the correct bracket. There are two crucial conceptual differences that has allowed us to go from this way of writing and the Hamiltonian back to a covariant Lagrangian. One is that you have two copies. You don't have just a pi plus, but you also have pi minus. And the second thing is that what this pi plus and pi minus are is these are not the natural variable whose canonical conjugates will help you get the Lorentz invariant Lagrangian. Remember, this pi plus pi minus were like some combination of pi b and del b. And it is in terms of this b's. And pi b, remember, pi b had this expression which had f sitting in it. So it is in terms of those guys that you can actually achieve a manifestly Lorentz invariant Lagrangian. So you have to sort of do a lot of variable change and field definitions, bonds, so on and so forth to actually see this transform. But these things are crucial. And with this, now you can sort of check that if you use the Hamiltonian equations of motion, right? You take pi plus dot the pi plus and h Dirac bracket. But you see that here it doesn't make any sense to just use H because pi plus is only sitting in H plus part of the H. So you might as well just simply make it H plus. And similarly with the minuses. These equations of motions with the definitions of pi plus minus that we have given before are precisely the one that I was writing down earlier. And of course, now it's going to be in a manifestly non-Lorentz invariant form. So you have to break it into those into the components and look into the spatial parts specifically and remember the gate choices to show that these are identical. But it's really the same. And here, coming to Rickard's point that he raised earlier, is that you see that H plus really is negative definite because it's a minus of pi squared. So it's really as Klaus was saying, that it's really a sort of something which really doesn't have a well-defined ground state. It's a negative energy. It's a ghost. But it's not a ghost in the sense that it's not a Fadil-Popov ghost. It's a reason the ghost in the original definition of the word, which is somehow probably got lost in something which is a negative kinetic energy.
So so now it's clear why you chose the minus sign because you knew that the part that decouples, so to speak, that doesn't take part in the interaction will get the wrong sign, and then the interaction will be okay.
Yeah. So then the point is that even though it has negative definite energy, we don't really worry about that because that part of the Hilbert space or that part of the Hamiltonian is not something very interesting. Since the Hamiltonian has nicely decomposed, the Hilbert space is going to nicely factorize. And you can always project out the part which is corresponding to this additional degrees of freedom. They are always, the H plus is never going to see H minus sectors, H minus is never going to see the H plus sector because this. Now the quantization part is clear, right? You promote this to commutators, there is no further obstacle. Right? You have done all the constraints and solved everything. Just promote this to commutators, and if it's a free theory, you expansion integration and you have the result. I mean, we will do one such example later down on the road, but right now the whole point is that the interaction, essentially this is describing a free cell-to-cell scalar, cell-to-cell form field, but with a negative definite kinetic energy, and an interacting cell-to-cell thing, but the interaction is constrained only to be something which depends on this Q field and not anything else. Okay, so how long do I have? I'm going on for quite some time.
I mean, however you want. I don't think I have this here after. I'm not sure.
So maybe
last time you went over another because of so.
Yeah, but I should not sort of indulge on hospitality.
I think you should just find a good point to stop because I guess you're not going to give all 4 lectures now.
No, yeah, but there's one small comment that I can make, and then maybe that's because then it will nicely round off the whole quantizations too. Then of course there are some explicit computations we will do, but the formalism part is complete. The thing is that at this point you might sort of wonder that why is it so easy to see the decoupling into the Hamiltonian picture and why can't we see it in the Lagrangian picture? One very short answer is that simply because the Lagrangian, what makes it manifest in Lorentz invariant, those field variables are not the one which has the right field variables to see the decoupling. That's the essential crux of the story. But it would be nice to know that the Lagrangian also sort of decouples in some sense. So one quick way of seeing that the Lagrangian also decouples is that now that we have the Hamiltonian decoupling, you can look into the first order action itself, the phase-space action, the phase-space Lagrangian. That is very easy to do, right? You just have the reverse Lagrangian transformation. And that you can also show that it decouples. So very quickly speaking,
yeah, that's just because you get a PQ dot term, and that's again plus minus.
Yeah, exactly. So you have this. You have this thing, right? Now, and this is okay. Explicitly, this is. I think it's maybe both. Remember, we have this constraint that del I pi b I j is 0. One way to solve this constraint is essentially sort of introducing a new field, b tilde. B tilde is some other form. And if I write pi b as some epsilon del b tilde, then you see that if I act with another derivative on here, the epsilon contracts with two derivatives. That's identically 0. So this definitely solves the constraint, this way of writing. Okay. And what this does is that if I have the pi plus minus expression somewhere? So the pi plus minus expression, just to remind you, it had pi b and it had epsilon del b with a total of half factor. This simply becomes epsilon del b tilde epsilon del b. Okay. Now the claim is that this the Hamiltonian first and foremost.
Well,
Plus minus.
plus minus. Yeah.
Plus minus. Yeah, that's important. So this Hamiltonian has a symmetry under which b tilde goes to, in my convention, minus p, and b goes to minus b tilde. So which is essentially pi minus going to itself and pi plus going to negative of pi plus. And it's very easy to see that Hamiltonian doesn't change, right? Because h plus was just pi plus squared, so it doesn't care if pi plus went to minus pi plus. And pi minus doesn't change itself, so it remained the same. So under this parameterization, the Hamiltonian part has the symmetry that b tilde change to minus b and b change to minus b tilde is the same. This is really nothing new. Done in a Lorentz covariant fashion, this is essentially like trading b with its Poincaré. It's a standard manipulation that you do. It's just because it's in a phase space variables, things are with like ij's and so on. So it's just making the manifestation of that. But now the claim is that this guy, this guy is clearly not invariant under the exchange of b and b tilde and b and minus b tilde. But the action is, because this guy is, so if I define it, say, so this after using this constraint is essentially epsilon del b tilde ij del 0 b ij, right? So let me call this something like k b tilde b. And you can easily show that this is equals to k b tilde plus time derivative of epsilon b tilde b space derivative epsilon b tilde. And of course, if Lagrangian was all that we were interested in, then I couldn't proceed further. But ultimately, what matters is action. And we are in flat space time, so you can drop this total derivatives. So the level of action, this guy and this guy are really the same. And you can make them more manifest by simply writing the Lagrangian in a more manifest fashion. You can just simply write it as half k b tilde plus half k b tilde b minus whatever we have upstairs. Now the Lagrangian looks manifestly symmetric in b and b tilde. And now we do one further variable transformation, which is we define b tilde plus minus b to be small b plus minus. And then it's just the two lines of calculation to show that this nicely separates out into something a b plus b plus and this Hamiltonian. Under this, remember this pi plus simply becomes epsilon del b plus and pi minus simply becomes epsilon del b minus. So this is purely a function of plus, and then there is a P a function of B minus. And now at the first order Lagrangian level, you can also see the decoupling happen. What this is good for is when you do something simple that we don't really think twice about in an ordinary case. For example, I start off with a higher dimensional theory and I do a dimensional reduction. If I don't show this, it's a bit of a problem because I have an extra field. And if you do naive dimensional reduction, because of the cross term, you're going to get naively terms which are like unphysical, unphysical, physical, physical, and then unphysical, physical itself in lower dimension. And you might wonder that whether this dimensional reduction sort of maintains this or not. Or you have to always go to the Hamiltonian picture in the lower dimensions and then repeat the analysis again and again. The fact that you can already show this at the level of Lagrangian tells you that you don't have to worry about that. Even in the naive original variables, it doesn't look decoupled. It's always okay to just focus on the physical sector and forget about the unphysical sector. The decoupling is there. You're just not using the right variables to make it transparent. So that's what it is good for.
Can't you just go on and integrate out the moment and just get back to the ordinary Lagrangian, but in a separated way? Because since everything is separated, it should stay separated.
Yeah, the only problem is that the variable in terms of which these are separated are not the variables in terms of which the Lagrangian has a manifestly Lorentz invariant form. That's the problem. Because at the end of the day, I want to do standard Feynman diagram computation starting from manifest Lorentz symmetry, and I don't want to think about all these things.
So somehow you're back to this problem with keeping Lorentz invariance.
Yeah, keeping it manifest. Because if I'm doing some sort of 5 index objects, I mean, if I don't have Lorentz symmetry manifest, I could make a huge mistake and won't realize like after it's too late.
Yeah.
But then a good point is that in position space, this is the Lagrangian, this decoupling. Seeing this, we have to do all this work that we did for 2 hours. Not in next lecture, but in next to next lecture, I will show you that the decoupling can be seen much more easily if you work with the momentum space action, which is extremely good news because I don't know about you, but I always prefer to do Feynman diagram computation in momentum space. So there we don't have to jump through all these hoops. But okay, it's good to know that because covariant canonical quantization is still the most rigorous way of quantizing. So it's good to know that the decoupling is something that can be rigorously established. But for practical computations, you don't need to repeat all these steps. Okay. So to complete the formalism, the next lecture, we are going to take the next non-trivial step, which is so far every discussion has been in flat space time. As I keep on saying, the quintessential example is type 2B supergravity. And I have not yet shown you that this formalism gives you the same type 2B supergravity equations of motions, for example. That would be one consistency check, right? And how do I know this is the correct formalism? I should reproduce at least that. But prior to that, I have to know how to couple to gravity. And the very basic problem is that if you naively couple this thing to gravity, things are all hell are going to reduce. Because you have a negative definite energy sector. If you make that gravitate, then things are going to be very bad. So somehow we have to find a way. The guiding principle is the same. We won't let the additional field talk to any of the physical field sector, including gravity. So somehow we have to find a way to couple to gravity only the H minus sector, whereas the H plus sector should be left alone. And that would have interesting consequences for what kind of diffeomorphism property does this objects have. How do I show that action still has diffeomorphism invariance and stuff like that. And this is the third and last unusual feature from a field theory perspective, that you don't couple to gravity in a standard way, just replacing eta by g and the derivatives by covariant derivatives and stuff like that. You couple it in a very different way. And I'll again explain that why this is something expected from the string theory side, but of course, very unusual from the field theory side. And that will complete the formalism next lecture, and then in how many lectures you want after that, we can discuss explicit computations for various kinds of theories. Okay, so I think this is a very good stopping point.
Just feel free to ask questions or comments.
Could we have seen this decoupling of the H if we had not used the pi plus and pi minus variables, instead going with the original ones?
No, that's the thing. I mean, if we could have, I wouldn't have gone through.
Yes, I mean,
For sure. That would have been really ideal, but then that should also tell you that that would mean that this is like a really simple textbook kind of problem. Like this shouldn't have stumped the community for decades, right? So some weird thing had to sort of go on to see this decoupling. But also there is something here that I like to think of is that this is really a sort of new approach, so to speak, in writing down an action. Right? Typically, when we think of writing down an action, we identify what are the degrees of freedom, what are the symmetries, and then write down the most general possible term consistent with that symmetries using those degrees of freedom. This is doing something more. This is saying that, okay, I'm not going to write down an action for the degrees of freedom I'm interested in, but for an enlarged space. But in such a way, such that this enlargement is kind of trivial. Like at the level of phase space, there is a nice foliation that happens. And this is something very special. I mean, it wouldn't happen for arbitrary interactions for arbitrary fields for sure. And I would say that at the level of formalism itself, this is not something that is very well understood. That we know this works, but to what extent will this continue to work for what other kind of fields and etc.? That is something, a question you can ask. And then it will get even more interesting when you start coupling it to gravity.
Does it make sense to compare with previous approaches before sense? I mean, for instance, is the PST formalism too far away to make sense to make a comparison, or can you?
Yeah. So as it happens, only last week there was a paper which showed that apparently this formulation is, at least there's a connection to the PST in some. The PST has to be done in some gauge and this has to be reduced in some way, but there was a connection that was made. But one thing that I would like to say is that as far as I understand, PST, we know in principle it can be quantized. But apart from very simple free theories, nobody has actually explicitly quantized any very evolved theories of chiral bosons in PST approach. They have done a lot of writing down classical equations of motions or writing down the classical field theory. But that's it. And I would say that at the level of off-shell, this is something. This is a point of debate. I should say that there is not everyone in the community is in the same holds the same opinion as me, for example. But the point is that you see all the other approaches like PST or Subhroneel or any other approach that you might think of. Chirality or self-duality is really an equation of motion. It's something that you derive as an equation of motion. And there are auxiliary fields needed to impose that as an equation of motion and so on and so forth. Here, the chirality is really part of the definition of the field itself. It's simply saying that there is a very nice tensor field itself, which is self-dual or anti-self-dual. And I don't need to define something bigger than that. And I can define really interactions and everything indirectly in terms of it. Now, my problem is with the other approach is that if I have del plus phi equals to 0 as an equation of motion, and this is a free equation of motion, and then I really introduce an interaction, then my equation of motion will change to del plus phi equals to some v of phi or some other thing of phi. Then I really don't have chiral boson, so to speak. You have something which is chiral in the free limit, and then it is interacting, and then therefore it's not really a chiral boson. So I don't know for non-free theory what does it even mean in those approaches. So one example that I can discuss is that one thing that we looked into is this TT bar deformations of this written in sense approach, right? The moment you start with a Fourier Jackie and do a TT bar deformation, it becomes an ordinary boson just after the first truncation because it loses its identity as a del plus phi equals to 0 and del minus phi equals to 0. That's not true anymore. But for our case, A is always going to be self-dual and B is always going to be anti-self-dual, but the stress tensor will make them interact with each other. And you can do computation because TT bars are very well studied and they have lots of general properties. So any TT bar deformed QFTs will have some general properties. You can do explicit computations and see if you're reproducing those properties, and we could. So that's a consistency check, so to speak. But okay, I mean, the PST community sort of keeps on telling that, in principle, if you can do the quantization of PST, somehow you're going to end up with the same theory. But I guess it might be true, but unless somebody has explicitly done quantization for free theories, yes, free theory, everyone can do everything, like, and all answers match. Everything is quite peachy.
So, could you rewrite this in spinor formalism? I mean, self-dual fields with spinners are somehow nicer, or you can see that they are representations in a more natural way, maybe. So you could hope that if you rewrite it in spinor formalism, things would look more natural.
Yeah, could be. I don't know. In fact, I don't think anyone has tried to rewrite any of this in spinor notation, so to speak. Once we discuss the coupling with the curve diagrams, I think one thing could be that it might be a little bit tricky there, but okay, it might still work out. It's just that nobody has looked into it.
Mm-hmm.
What people have looked into is that constructing supersymmetric theories with this, because one of the things of interest where chiral bosons appear is this d equals to 6, right? Whether it's supergravity or infinite wall volume theories.
Right.
So people have constructed like candidate like Lagrangians or actions with 0,1 supersymmetry, 0,2 supersymmetry, and stuff like that. So
why only candidate?
Why only candidate? Because they don't satisfy all the things that we would expect out of multiple limb-fibril volumes. So, for example, one problem people have not somehow able to manage out, figure out is that how to find a non-abelian generalization of this, which you would need if you have multiple limb-fibrils.
Right.
So that is, I think, there are some work in that direction, but as far as I understand, the final word has not been
said. Yeah, you don't even need to have self-dual fields to have problems with non-abelian higher forms. I mean, that's,
yeah, of course. I mean, but hopefully, but there are some indications why this might be a good thing, and I'll discuss some of them. So, Neil Lambert has a very nice paper where he discusses these aspects. But some problems seems to be addressed by this formalism, but not all of them. There is something new that still needs to be put in. But for sure, this can be supersymmetric, of course. So this is fine with supersymmetric. You can have supergravity, Lagrangian actions. Now you can finally fully write. Yeah, so I mean, just to summarize your question, for free theories, other approaches, known things, these reproduces, but then this goes beyond. But the other ones, they can't even compute, so I don't know how to compare. That's it.
There are no further questions. Thank you, speaker. We'll go to the next speaker.
Yes, sir.